Okay, another lockdown video. Lockdown doesn't look like it's ending soon.
Mm-hmm.
Yeah. So let's deal with a topic that we spoke about in our recent book, The Cosmic Revolutionaries Handbook. And oh, there it is.
Oh, there it is.
Looking good. So
I should say I do this in every Zoom meeting I'm in. It happens to be what we're talking about here, but every time I just.
So both you and I, of course, do astronomy professionally. We give public talks, etc. And one of the things that we get is we often get an email or a letter from a member of the public with a new idea about how the universe works. So if I'm one of those people, I send out my letters. I know that I basically get no response. Why? Why won't scientists listen to my revolutionary ideas? What happens, Luke, when one of these pops onto your desk?
Yeah, let's just give you the view from the other side, just in case you're one of these, you ever think of a revolutionary theory, you want to send it around. So what happens is I get an email from someone I don't know, and they say, the typical one goes like this: "Hi, I have a brand new theory of the universe that's going to revolutionize everything. I've been working on it for 20 years," is something they often say. Somewhere in there, there's very often a little something like, "I'm not a mathematician," or "I haven't worked out all the mathematical details." That's often in there somewhere. But could you... Often they don't even ask. They just go, "Here's this theory. Obviously, it's the greatest thing." But if they do get around to asking something, they'd be like, could you have a read of it and tell me what you think, is the nice end of what they say. Otherwise, it's, how can you arrange for this to be published in a journal somewhere, and then, and so that's the sort of email that we get.
I also have gotten a few written letters with "Do not share this with your government." Written
Oh
on it.
yeah, classic. Yeah. Yeah, the written manuscript is one that often gets sent as well. And so here's what happens. So I'm going to pull up on the screen now a website called the Archive, and we're going to go to the page of the Archive, which is just the number of astronomy papers that have been published today, and we're just going to notice how many there are. And so, as a professional astronomer, I've got to keep up with the latest ideas, and those are in the form of published papers. And when we publish a paper, we put it on this website to get it out there, as well as being published on the journal, the individual journal pages. Those have been proofread. This is just the preprint version. And so today, if I wanted to read all of that, there's probably more stuff than I could read today. And so I've got to be selective about what I read. And so straight away, can you read this thing that I sent you? The answer is probably no, just as a blanket thing. Like, I've got to have some good reason why I want to read this, rather than something that was actually published in an astronomy journal. So just as a, why aren't people reading my thing? There's step one. It's because we have a lot of stuff to read, and your stuff didn't make the list of stuff that's published somewhere. And so right off the bat, that's a bad sign. However, I will just flick through your email. I might even open up the attachment to have a quick look. Very rarely does that change. So my initial assessment is, I'm not going to read this in detail unless there's something pretty impressive here. Very rarely does the thing I am sent change my mind, for various and sundry reasons, which we'll go through at the moment. One of them is, a particularly bad sign is, there's a wonderful website that I'll link to, which John Byers, the mathematician and physicist, put together, just called the Crackpot Index. There's a whole lot of standard lines that you get from crackpots when they send you an email, or when they email you something, and he gives them a whole bunch of points. Now, you start off with -5, so you're allowed to break a couple of these rules and still not have a positive score. But as you go through them, it's things like, I'm being treated the same way Galileo was treated, I'm the next Einstein. A particularly bad sign, which I see quite a lot, is if you have already named your theory after yourself, and you're talking about it as if it's an established theory or result or whatever, or equation, and you've call it, if I send around emails saying I've discovered the Barnes equation, like I'm sure you have discovered the Barnes equation, but the way that works in academia is you put out your work, and if it becomes so valuable and highly cited and highly regarded that your fellow scientists need a way of referring to it in a compressed way, they might begin to attach your name to it. So it'll be called the Barnes theory or the Barnes equation or the Lewis equation or whatever. It's supposed to happen organically because your work is so good that others have recognized it. Putting your own, just shortcutting all of that and saying, hey, here's the Barnes equation is a really bad sign of someone who has not really thought too hard about their own theory.
So again, I think this is another thing that we see reflected in these emails and letters, is that the writers often have a very poor understanding of what science is, how science proceeds, and what has been done in the area before they came along.
Yeah.
Right. So, there's no references to any other works. There's very little references to observations and data, etc. So again, that's a real big warning flag that this is a person who doesn't know the field, and you can't revolutionize the field unless you know it.
Yeah. A classic mistake is to attack the first bit of observational evidence for some idea. So here's a classic one, the Big Bang Theory. The first bit of observational evidence was basically the Hubble diagram. So Edwin Hubble discovered that the amount that light is stretched, that increases the further away the galaxy is that you're looking at. So if I see a galaxy a certain distance away, I see that its light has been stretched by a certain amount. I look twice as far away and it's stretched by twice as much. If you look at the first data, the first observations that showed this trend, they aren't massively convincing. It's a bit of a scatter plot all over the place. There's only 20 or 30 points on the diagram. And, I actually read someone who's criticizing, who's saying, making a case against the Big Bang Theory, who said, look, this evidence isn't that good. Actually, these cosmologists, they draw a straight line through it, but actually a slightly curved line fits the data better, a quadratic instead of a linear line. And the answer to that is, okay, that was in 1929 that data was first published. We've done a lot of stuff since then. One of the reasons we wrote our book was precisely to give the most recent observations that you've got to deal with. That was 30 nearby galaxies. We now have surveys of millions of galaxies out there in the universe. And so we have observation. We don't have distances, independent distances for all of those galaxies, but we have a lot more data to deal with that you've got to handle. And so, as Geraint said, if there's no reference to the latest data, there's no reference to what people have done. If you're trying to pretend like you're the first scientist ever, then that's a real big red flag.
And what about the lack of mathematics?
Oh yeah, this is a classic. I got this at the end of last year. I look for this line every time I get an email. It's not always there, but it's something like, I know my idea is correct. I just can't do the maths. Or, I'm a this, not a physicist. I'm a that, not a physicist. And so I can't quite do the maths. The reason why this is a problem is, in a lot of cases, the prediction, the data that you have to explain, and that's, if you're not doing that, you're not doing science. We have observations of the universe. And if you want to tell us what the universe is like, it better be consistent with those observations. And those observations are, for the most part, measurements. They're not just trends or concepts or ideas, they're numbers. And so there's a relationship. There's relationships that you have to explain. And so if you want your theory to predict numbers, there's got to be maths in there somewhere. Now, you might have an interesting concept of the universe, which if you thought about it, you could translate into mathematics and then you'd have a theory. But if all you have at the moment is the concepts, you have no idea whether you can explain the numbers in detail until you actually do the maths and work it out. There is a particular relationship, between redshift and distance. And in particular, it's linear, it's a straight line for small redshifts, and then it changes at small distances, and then it changes. And you've got to deal with this bit and then that bit in detail, exactly how fast. All of that stuff. You have no idea whether your theory works until you can do that. Now, the problem is people often think of that as being just physicists trying to protect their turf. Like, if you're not doing it the way we do it, then I'm just not comfortable with that. And then, that's just them trying to gate off their community from outsiders. And the answer is no. If you want to explain the universe, you got to explain the things we know about the universe. And a lot of the things we know about the universe are measurements. They are numbers. If you've got to explain numbers, you've got to do maths at some point. And so, you can't get by without doing maths.
Yeah.
And if you can't do the maths, then you haven't got a theory yet.
So, you know who I blame?
Who do you blame?
I blame Einstein. So why do I blame Einstein? That was your line, by the way.
Line. Okay.
So again, in the public portrayal of science, right, especially portrayals of relativity and the foundations of relativity, and there's always a big discussion about how much Einstein relied on his Gedanken experiments, right? His thought experiments that you do in your head. And I often get the feeling that people think that part is the science part.
Yeah.
Right.
Yeah,
and it's the kickoff, right? You have your idea and you ask yourself, right, what are the consequences of my idea in terms of how we observe the universe or how we do experiments? And then you develop the maths. So the story about how Einstein went from, if I'm falling off a building, gravity disappears, into general relativity, seems to miss out that bit where, he had to learn about curved space-time and tensors and all this kind of stuff. That part often gets lost from the story. And it's the thought is that if I do the Gedanken experiment, if I have my thought experiment, my concept, and it's pretty cool, I've done the hard bit.
Yeah.
And that's never the hard bit.
There's some quote from Einstein that I've never quite... So he said, "Do not worry about your difficulties in mathematics. I can assure you that mine are still greater." And that's an ambiguous quote. I don't know what he meant. I've got to... Someone tell me, did he mean, don't worry if you find maths hard, I find maths hard too? Or did he mean, stop complaining about fractions, I'm trying to do tensor calculus here? And it's ambiguous between those two. But the point is, Einstein, he spent basically 10 years finding the best mathematicians in the world to learn a particular, brand of, it's called pseudo-Riemannian geometry, high-powered, the most high-powered maths he could throw at this particular problem, and he had to, in order to formulate his theory, he had to learn a mathematical language to try and say the thing that he wanted to say. And it's only because he did that, you can't use Einstein's thought experiments to work out how much light will be deflected as it goes past the sun. That's a prediction of Einstein's theory, but it's not a prediction of any thought experiment. You might be able to predict that it will be bent, but if you want to know by how much,
that's right.
Go do some maths.
That's right. So yeah, I think we tried to get this concept across in the book. Yeah, I don't want to pick you up on something here. I think you said pseudo-Romanian. I don't think... as in this, something like Romania.
Romanian. Riemannian.
Riemann.
Yeah, Riemann. Pseudo. Yeah. I'm gonna put his picture on the screen. It's a country next to Romania called Pseudo-Romania. They have really interesting geometry there. No, there's a famous mathematician, Riemann, or Riemann, who knows? And so one of the things that the mathematicians were doing in the 1800s is working out how to do geometry very precisely and generally and handle any sort of curved spaces. And as a part of that, you can extend out to weird sort of spaces that aren't just your usual geometry of the world that we live in. And so part of that extension is this particular field.
And actually, what I think is really cool, and I explained this, I'm teaching general relativity in the coming semester, is the names that you hear in general relativity are often the names of people who worked on geometry, not physicists. So Riemann never worked on relativity. He died before relativity came out. Christoffel and Levi-Civita and all those names, they're all names of people who worked on this form of geometry, which Einstein realized was his toolkit to build his theory, right? And I said, it's that notion of you've got to, it's mathematical. That's what it is.
And even then, so I've been sent papers, actually to review from a journal, and it said it was trying to make, anyway, the point was it wanted to say something about the way waves work, but the equations it applied to waves as a wave phenomena were just the standard high school equations out of any high school textbook, that the wavelength goes like 1 over the frequency, and it will change its direction when it hits it. It's called Snell's law. But it just used those equations, just high school level algebra equations, not obviously not realizing or not bothering to say, like, there's a theory that has to produce those equations. There's a theory about how the world works that then those equations come out of. You can't just take the equations that describe water waves and stuff and just smack them into your model and think that you've got a sophisticated model. Then it just looks like a hodgepodge of the physics the high school level algebra that I can actually do, and nothing more advanced than that. So that's another bad sign. It
is a bad sign. So what's our takeaway message? We should probably wrap this up.
Two things. If you want a scientist, especially a famous scientist, to answer a question that you have, here's the way that you write that email. This is not a guarantee, but I'm just saying this is the best hope that you have. Just say, do the title as something like a question about, and then something that they've written, and then open up with, I read, and the book of theirs or the paper of theirs that you've actually read and you've actually tried to understand. And then you can ask a question about something that you didn't understand in there as a way of broaching that area and saying, what if it was, this, and then you can sort of give a hint towards what you think your theory is, or whether you think there's a hole in the data there or something like that. That, I think, is the best hope you've got. You've got one paragraph, spell everything correctly, and then say yours truly at the end, and just, that's your best hope. And you still might not get anything. The more famous the scientist is, the more likely it is that they're not going to answer your emails. But that's the one best hope. The other point that we make in the book is, look, there's a reason why we publish in journals. Anyone can send a paper to a journal. It's just got to be good enough, okay, to get past the editor and then to get past the referee. And yes, there can be all sorts of politics involved, but for the most part, I think when an editor rejects or a referee rejects a paper, for the most part, it's just because it wasn't up to standard. It didn't actually deal with what's been done so far. It didn't actually present a mathematical model. It didn't actually compare that mathematical model with the data. It just didn't do the things we know you need to do to actually study the universe. So that's got to be your standard. You've got to get your model into a state where it's good enough to send off to a journal.
I think that's very sound advice. I'm sure we're going to come back to this topic again.
Yeah. Oh, one more thing. This is really important. We wrote a book in which we said, actually sending a random email with your 10,000 page Word document of your theory to just some random scientist saying, can you read this and then publish it and promote it and make me famous? Sending that email probably isn't the best idea of how to promote your theory. And as we've talked about the book, some people have taken this as an opportunity to send us their theories via email in the form of a 10,000 page Word document. Okay. the wonderful thing about this, and I encourage any cosmologist or physicist listening to do the same, what you can say to that is, hey, have you bought this book and read it? And at that point, we just, they can just go and, promote our book for us. Invariably, they haven't, because if they had and actually understood it and, taken it on board, they wouldn't be sending us an email.